In today's lesson, we're going to revisit the topic of moments. Recall that a moment is a tendency of a force to twist or rotate an object. Consider the following. Next time you close the door, try pushing on the door near the hinges. Now try pushing the door closed using the handle. What did you notice? You probably saw that it was much easier to close the door pushing the handle. Now try closing the door by pushing directly on the hinge. Why is there such a little movement? Think back to our study of mechanisms from Unit 1. Because you're pushing on a point at which the door rotated, similar to the fulcrum of a lever, you can push or pull as hard as you want, but the door won't budge. In essence, a door can easily be opened using the handle because only a small amount of force is applied at a greater distance away from the door's hinges. Therefore, it becomes increasingly difficult to open a door the closer the force is to the hinges. Recall that in our discussion of moments, the moment of a force is the measure of the tendency of that force to rotate the body upon which it acts. In this example, you can see that a force is applied to drive the bolt, producing a measurable moment, and the wrench rotates about the axis of the bolt. When it comes to calculating a moment is generated when a force F acts on a perpendicular distance d, which originates at the fulcrum. The formula for calculating a moment is force times perpendicular distance, or m equals F times perpendicular d. Recall that in the English system, the units for a moment are commonly expressed in foot-pounds. However, in the metric system, moments are commonly expressed using Newton meters. Both sets of units for moments will be used throughout this section. Now let's talk about rotation direction. Recall that with forces, any force that is going to the left or down is considered to be a negative force. Any force that's going to the right or up is considered a positive force. In a similar situation, when we're adding moments, it's important to know if the direction is clockwise or counterclockwise. We're going to use counterclockwise for positive moments and clockwise to represent negative moments. When it comes to determining whether or not a moment is going to result in a positive or negative rotation, we can apply the right-hand rule. To use the right-hand rule, you're going to curl your fingers to match the direction of the rotation. If the thumb is pointing up or towards you, it's going to result in a positive counterclockwise moment. If your thumb is pointing down or away from you, it's going to result in a negative or a clockwise moment. In the example on the left, you can see that we're using a downward force applied to a wrench in order to loosen a bolt. When we apply a downward force using the right-hand rule, you can see that when our thumb is going to point towards us, which is going to create a positive or counterclockwise rotation. In this example, you can see again that we're applying a downward force to a wrench in order to tighten a bolt. When we apply a downward force using the right-hand rule, you can see that our thumb is pointing away from us, causing a negative rotation, resulting in a clockwise moment. Let's go ahead and look at a few more examples of moment calculations. In this particular problem, we're applying a downward force of 20 pounds to a wrench with a perpendicular distance of 9 inches. To calculate our moment, we'll use the formula moment equals force times perpendicular distance, so it's 20 pounds times 9 inches. However, we need to convert 9 inches to feet in order to use the correct units. So 9 inches is equivalent to 0.75 feet, and if I take that value and multiply it by 20 pounds, I get 15 foot-pounds. Now notice the direction that the force is heading around that point of rotation. It's going to cause a clockwise moment. Therefore, our answer needs to be negative. So for this particular problem, our final answer is that we have a moment of negative 15 foot-pounds. Now let's look at another example involving a much longer wrench. We still are applying a downward force of 20 pounds and the perpendicular distance is 1 foot. So if I do force times perpendicular distance, I get 20 foot-pounds. However, since this downward force is being applied in a clockwise motion, we know that this moment is going to be negative. So our final answer for this example with the longer wrench is that our moment is negative 20 foot-pounds. In this example, we're now applying an L-shaped wrench to tighten a bolt. Notice the applied force is in the right direction at 20 pounds, and they give us two different distances, 3 inches and 1 foot. We need to figure out which distance to use. Since our applied force is in the horizontal direction, we need a perpendicular or vertical distance. In this case, we'll choose the 3 inches. So I'm converting 3 inches to 0.25 feet, times it by its perpendicular force of 20 pounds, and we get 5 foot-pounds. Again, using the right-hand rule, you can see that our horizontal force being applied about this point of rotation is going to result in a clockwise moment. Therefore, our moment needs to be negative. So our final answer is negative 5 foot-pounds. Now you can see that we're applying a Z-shaped wrench. The applied force is 20 pounds in the downward direction, and we have, again, two different distances, 9 inches and 18 inches. Since our applied force is downward, we need a perpendicular distance that's horizontal to the point of rotation. So we are going to choose the 18 inches as our perpendicular distance. I'll convert that 18 inches to feet, and I get 1.5 feet, times it by its perpendicular force of 20 pounds, and I get 30 foot-pounds. Again, with this downward force about that point of rotation, that's going to yield a clockwise moment. Therefore, our final answer needs to be negative again. So for the Z-shaped wrench, our moment is negative 30 foot-pounds. Now in this example, you can see that we have a wheel and axle system. The wheel has a radius of 50 centimeters, and we're applying a downward force of 100 newtons. Since the force is perpendicular to this distance, I can convert 50 centimeters to meters, and that's 0.5 meters, times it by its perpendicular force of 100 newtons, and we get 50 newton meters. So it's super important that you pay attention to the units and determine whether or not you need to convert any of these units, whether that be foot-pounds or newton meters. So in this example, again, we have our same wheel and axle with a radius of 50 centimeters. I need to convert that 50 centimeters to meters, so that's 0.5 meters. However, in this problem, we see we have a diagonal force of 100 newtons. To calculate our moment for this wheel and axle system, we need to find the vertical force since there is a given horizontal distance. So I need to calculate the force of this vector in the y direction. To do that, I'm going to do 100 times sine of 50, and I get 76.6 newtons. Times that by our perpendicular distance we found before of 0.5 meters, and we get an answer of 38 newton meters. Since the rotation of this force is going to result in a counterclockwise motion, our moment is positive. Let's quickly review what equilibrium means. Equilibrium is the state of a body or physical system with an unchanging rotational motion. This means that there's two cases. One, the object is not rotating, or two, the object is spinning at a constant speed. Either way, the rotation forces must be balanced. For this to happen, the following conditions must be satisfied for a body or structure to exist in a state of static equilibrium. 1. All forces or components of forces must sum to 0. In two dimensions, we must consider both the x and y components of these forces. Therefore, we can break down the sum of the forces into the sum of the forces in the x direction and the sum of the forces in the y direction. 2. All the moments about at any given point must sum to 0. This is represented by the formula listed at the bottom of the slide. It says that the sum of the moments has to equal 0. So if I add up all my moments, whether they're clockwise or counterclockwise, they need to be in balance. Here you can see we have a seesaw with two bears sitting on opposing sides. You can see that the bear on the left is smaller and weighs 25 pounds with a perpendicular distance to the fulcrum of 4 feet. The bigger bear on the right weighs 40 pounds and has a perpendicular distance that's unknown. To solve for this unknown distance, we can set up a formula for using our moment calculations. We can say that 25 pounds times 4 feet is equal to 40 pounds times x. And if I solve for x, I get 2.5 feet. Now that same process can be applied to many different types of problems. Consider this example below that involves a loaded beam. Here you can see that we have a beam with two joints, joint A on the left, joint B on the right. There's two reactionary supports that are used to keep this beam up. We have RAY and RBY, respectively. Notice that there is a load between the beams that has a weight of 35 pounds being applied in a downward direction due to gravity. The distance between RAY and our load is 3 feet. The distance between the span of A and B is 10 feet. We need to go ahead and set up our moment calculations to find the values of both RAY and RBY. To do this, we're going to need a point of rotation. Let's assume that A is going to be our point of rotation. If the gift is applying a downward force of 35 pounds, that's going to cause a rotation about joint A that's going clockwise. Notice that RBY will counteract that by rotating counterclockwise. Since the sum of the moments has to balance out to 0, I know I can set my counterclockwise moments equal to my clockwise moments. So at RBY, I have a counterclockwise moment, so I'm going to multiply that force RBY times its perpendicular distance to the point of rotation of 10 feet. So RBY times 10 feet equals 35 pounds times 3 feet. And if I solve for that missing value of RBY, I can see that RBY ends up being 10.5 pounds. And then since the sum of the moments also has to balance out in both the x and y directions, since we have vertical forces going on here, I know that the sum of RAY and RBY have to add up to the force at C. So I'm going to say that RAY plus 10.5 has to equal 35 pounds. And then I can solve for RAY and I get 24.5 pounds. Now let's extend this knowledge to our first truss problem. Here we have a truss that has joints A, B, C, and D, and beams AB, AC, BC, and BD. At joint A, we have a pin support, so we're going to want to replace that with the two reactionary forces in both the horizontal and vertical directions. We'll call that RAX, RAY. And at joint D, we have a roller support, which gets replaced by one reactionary support perpendicular to the surface, so we'll call that RDY. And then we have applied forces of 500 pounds and 600 pounds in the right and downward directions, respectively. They tell us the distances between A and C is 24 feet, the distance between B and C is 12 feet, and the distance between C and D is 8 feet. So to get started with this truss problem, we know that the sum of the moments has to balance out to 0. So I'm going to set my counterclockwise moments equal to my clockwise moments. Since joint A is a pin support, we'll call that our pivot point or point of rotation. So at joint B, you can see we have an applied force of 500 pounds that's going to cause a rotation in the clockwise direction. This is also true for the downward force at joint C, which is also going to cause a clockwise rotation. And then opposing those two forces is going to be RDY, which is going to rotate in the counterclockwise direction. So to set up my equation for making sure that all the moments balance out to 0, I can set my counterclockwise moments equal to my clockwise moments. So we can set 24 feet times 600 pounds plus 500 pounds times 12 feet equal to RDY times 32 feet. And then I can solve for RDY and I get 640 pounds. And then if I wanted to go ahead and solve for RAX, I could set any forces in the right direction equal to any forces in the left direction. To find RAY, I could set all my forces in the up direction equal to all my forces in the down direction. This would ensure for this particular truss problem that all forces in both the horizontal and vertical directions, as well as any moments, all balance out to 0.